We are quite familiar with how to plot points. If I wanted to plot the point 3, 5, for example, starting at the origin, I would go 1, 2, 3 units to the right, and then 1, 2, 3, 4, 5 units up, which would put that point right about here. But sometimes that's not a convenient method. For reasons that we will learn over the course of the next few sections, sometimes it's easier or more convenient, or it makes more sense to kind of go about this a different way. Because we're dealing with trigonometry here, what if we wanted to talk about how far this point was from the origin directly? In other words, what is the length of that segment right there? Well, I'm going to call that r because that just makes sense. And then again, because we're talking about trigonometry here, I'm going to take a look at this standard angle here. We're going to call that theta. Another way to describe the coordinates of this point right here are as the radius, how far out do I have to go, and the angle, how far around do I have to go. Let me move that over. And it turns out I can't move the 3, 5 without moving more than I really want to. So I'm going to erase it and rewrite it here. And I'm going to label that x, y. These coordinates we are comfortable and familiar with. We call these rectangular coordinates or Cartesian coordinates. In fact, let's move things around just a little bit more and I'll actually label them. These are either rectangular or Cartesian. And coordinates that look like this are called polar coordinates. I'd like to reorganize this screen a little bit here. I'm going to make the left-hand side of my screen over here about rectangular or Cartesian coordinates, and the right-hand side about polar coordinates. So give me just a second. All right, now I have everything on the screen that I want, and you have to watch while I move things around a little bit. Okay, that's not too bad. So in summary, rectangular coordinates are a description of a horizontal and then vertical change from the point on the graph that we have traditionally called the origin. That's not a very vertical line there, I've just realized, but pretend with me, won't you? Polar coordinates are a description of how far a point is from 0, 0, but also of how far around it is from this axis. And we're going to call, in polar coordinates, we call this point right here the pole, where in the rectangular or Cartesian coordinates, we called this the x-axis. We're going to call it the polar axis. I guess I could label this x-axis since we're giving it a name. Now, in polar coordinates, this angle can be anything. It can be pi over 6, pi over 4, pi over 3. This looks like it might be about pi over 3, pi over 2, and so on. It can be 2 pi, or it can be 0. It can be pi. It can be 3 pi over 2. It can be any known common value, or it can be an uncommon value. It might be pi over 12, or it might be 2.4 radians, or it might be 6.7 radians, which would actually be a little more than a full circle. The thing is, because we're going to be traveling in radians, it might actually make more sense here. Instead of having an x and y axis, a horizontal and vertical axis, those can be handy, and we'll leave them as part of the picture. But in addition to that, let's mark our common angles in the same way that I'm going back over to my rectangular coordinates. If I wanted to graph the point or plot the point, let's use green, 1.5, 2, I would have to use these tick marks, 1, 2, and estimate about where I was between 1 and 2. I'm kind of estimating between 1 and 2. Halfway is right about there. And then from there, I'm going to go up 2. So that point would be about here. And I've used these integer tick marks to help guide my decision about where to plot that point. And I'm going to do the same thing here. I'm going to graph some common angles. Just going to put in some guides here. Let's see, I want to do this. Maybe I'll do dotted lines. That looks like about pi over 4. And there would be about pi over 6. And then I'll do the same thing in the other 3 quadrants. Now this isn't very pretty, but I'm just trying to give you an idea. For example, now if I wanted to graph the point, let's do a point in actual polar coordinates. If my theta ends up being pi over 2, say, and my radius ends up being 4, then I can think of it one of 2 ways. I can think of it as going out 4, 1, 2, 3, 4, and then around to pi over 2, or I can think of it as going out around to pi over 2 and then going out 1, 2, 3, 4. Either way, that point is going to end up here. I'm going to change my point so that it's in green so that it matches the green point I have here. I may use the same graph for several examples. I don't know yet. Anyway, the point here, no pun intended, is that you can think of how to plot this point as being how far do I go out from the center, from the pole, how far out do I go? And then from, having made that decision, when I think of it that way, which I don't usually, when I think of it that way, I usually think of it in terms of the positive x-axis or the polar axis. So I'm going to go out 4 and then around. Usually, though, I think about which angle, which of these lines I'm going to be on, and then from there count. So I know I'm going to be at pi over 2, go out 1, 2, 3, 4. And that's actually the most common way to do this. You could do the same thing. Let's go to the 3, 5 point, just to make the argument. We're used to going to the right or left first, and then up or down, right? We go horizontal first and then vertical. If we wanted to, we could think of it as 5, 3. We don't tend to do that for a variety of reasons. One is the convention that we read from left to right, and I appreciate that not all countries read from left to right, right? Not all cultures read from left to right, but the culture that established this standard did. And so we go from left to right, we do this direction first, and then this direction. So that's the same thing here, except that it tends just to be easier. We always write these in this order, by the way. We always write polar coordinates in the order x and then y, horizontal and then vertical. We always write polar coordinates in the order the radius and then the angle. So from left to right here, we're going to go, oh, I have to go out 4, and then there's 4, and then around to pi over 2. And that makes sense if you're reading from left to right. Just in practice, it tends to be easier, I think, to go grab your angle first. I know angle. Okay, now that I know which line I'm going to be on, I'm going to go out from the center 1, 2, 3, 4. That makes more sense to me. It's the way I've always done it, and I think it's the way most people I have worked with think of it. But anyway, that's the way that makes sense to me. You do it however you need to do it, but I think you'll find it easier if you think about the angle first and then how far out do I need to go. All right, now the other thing is the point that I plotted here, 4 comma pi over 2, is because it's on an axis, finding the radius was pretty easy. But what if I gave you the point, let's say 4, I'll stick with 4 comma pi over 6. Well, pi over 6 is this angle right here. And 4, well, where is 4 on that angle, on that line right there? It would be really helpful if there were some kind of guide that would let me know how far, what my radius was at any given point, right? So for example, if there was a circle here, I would know that that was the radius of one circle. If there were a circle here, I'd know I'd gone a radius of 2. Here's 3. Again, I'm doing a very rough, kind of pretty bad, pretty fast job on this because I'm just trying to make a point. Again, no pun intended. And then I'll show you a much nicer version of this. Okay, so far, the things that I have added to my XY coordinate system is some angle guide lines and some radius guide circles. So now when I go to plot the point 4 comma pi over 6, I'm going to go around, starting at the x-axis, to the angle pi over 6, and then I'm going to go out 1, 2, 3, 4. And those guide circles, wrong color, make it a lot easier for me to find where that point's going to go. If you Google polar graph paper and then click on images, you'll see just how many different versions there are of polar graph paper. It's not really paper, but you know what I mean. This is a Cartesian graph, Cartesian grid. This is a polar grid. It's really the same as the Cartesian grid, except that we've added these guide circles and the guide angles. Some polar graph paper just has a circle. It doesn't have any axes that extend. Wrong color. You know, you might see axes that extend beyond the outermost circle, or you might not. Most of them are just a circle, but they all include some guide radius circles and some guide angles. Some of them only include the pi over 6, pi over 4, and pi over 3 multiples. Some of them also include pi over 12 multiples. So you get an additional couple of guidelines in each circle, okay? In each quadrant, rather. Let's see, some of them include pi over 6, pi over 4. Some of them include labels. Others do not, because especially if you start with pi over 12, this is 0 pi over 12, 1 pi over 12. This is 2 pi over 12. That's pi over 6. This is 3 pi over 12. That's pi over 4. This is 4 pi over 12. That's pi over 3. So those are the angles we work with anyway. This is 5 pi over 12. We don't normally see that one. This is 6 pi over 12. That's pi over 2. So if we just add these pi over 12 additional lines, then you get a nice evenly spaced series of guidelines around through all of our quadrants. So if that's the case, and they're nice and evenly spaced, then we don't need to label them, because you, as the mathematician, will be able to figure out, oh, that's pi over 12, that's 2 pi over 12, that's 3 pi over 12, and so on. So sometimes they include labels, and sometimes they don't. I'm looking at one right now that only has pi over 6, pi over 3 in quadrant 1, and multiples of those. There's no pi over 4 multiple. So this one only has, it's missing all the pi over 12s, and it's also missing the pi over 4. Again, it's evenly spaced. So as a mathematician, I can look at this and go, oh, that's pi over 3, and that's pi over 6, and that's pi over 3. If I want pi over 4, I'll just add my own line in between. So there's lots of different versions of this. Sometimes the radius circles are really close together, and sometimes they're very far apart. Having them close together is nice if you work with a lot of large radius problems. Having them close together, having them far apart, makes more sense if you work with a lot of smaller radii. Or you can take one that's got the radii that are far apart and then use them to, like if I want, here, let me just do another point here. Let's use blue. Let's do 3.5 comma pi over 4. I know that blue is harder to read on the screen, and I apologize, but this is 3.5 and this is pi over 4. So using the technique that I was suggesting before, I'm going to go out to my x-axis, I'm going to go around the pi over 4 angle, and then I'm going to go back to the origin, and following that line, I'm going to go out 3.5. 1, 2, 3 and a half. I'm going to end up about there. So in the same way that I sometimes have to use the integer marks here to estimate what maybe 1.5 would be, sometimes I have to estimate what 3.5 is on the polar grid as well. And just to make it a little bit easier to see, that point is there. So the polar graph paper that you use will sort of depend on the context in which you're going to use it. If you work with a lot of very small radius problems, then maybe you want your radii circle to be very far apart, and then you're just going to use the guides, right? You're just going to estimate about what 1.9 a radius of 1.9 might look like. You can also get polar graph paper that's only the first quadrant. Sometimes it's labeled in radians, sometimes it's labeled in degrees, sometimes it's labeled in both. And as previously discussed, sometimes it's not labeled at all. So there's a lot out there. If I give some to you in class, it'll probably just be what I have handy. You're more than welcome to go grab some images off the web and see what your favorite is. Try playing around with it a little bit. There are some interesting variations out there, but they all have some commonalities. And those commonalities are that there will be an X and a Y axis, although they may not stand out, right? The reason there's an X and a Y axis is that there's always a 0, a pi over 2, a pi, and a 3 pi over 2. In between those, you'll either have a lot of guide angle lines, pi over 12, 2 pi over 12, 3 pi over 12, or you'll have a few. You might just have pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. You might have just the pi over 6s and pi over 3s. But you'll have some. They'll give you some. They may be labeled, they may not be. So there's similarities and differences. The trick is going to be finding one that's appropriate and that you're comfortable working with. Don't worry about don't spend any money going and looking for, big fancy notebook that's got polar graph paper in it. I'll make sure you have the supplies that you need for this class. But just be aware that there are a lot of different ones out there. Okay, let's take a look at what it really looks like when you graph polar coordinates. There are a few sort of variations, if you will, that we haven't talked about yet. All right, here's a nice clean polar grid, and we're going to try plotting some points here. We're going to plot the point 7, 7 pi over 6. We're going to plot the point 6, negative pi over 4. Those first two are from the exercise at the back of the textbook. This is question 6. This one's question 8. I don't have one of these, so I'm just going to make one up. I think I want to use 3 pi over 4. 3 pi over 4. Okay, so there are 3 points here. One with 2 positive coordinates, one with a positive r and a negative theta, one with a negative r and a positive theta. You can also have a negative r and a negative theta. And I know that the colors are sometimes hard to see on the black background, but hopefully they'll be easier to see on this white background. So I'm going to use blue to plot my first point. 7, 7 pi over 6. As I've said a number of times, I think it's easier to go around to the 7 pi over 6 angle guide and then go out 7. So let's figure out where 7 pi over 6 is. It might be easier first to put in some annotations here. This line right here is going to be pi over 2. It's really kind of hard to figure out where to put that. I didn't give myself a lot of space. But those are the 4 quadrant, what do we call those on? The quadrant lines. So that's pi over 2. Halfway between 0 and pi over 2 is 45 degrees, or pi over 4. That's not actually on a mark. That's okay. These two right here are pi over 6 and pi over 3. And now that I look at it, this pi over 4 doesn't look right, does it? It's halfway between pi over 6 and pi over 3, so it should be right there. So let me erase that and put it in the right place. Pi over 4 is this mark right here. So, and you can do that, let's see, halfway between there and there is this one. This line looks slightly darker to me than the others. The pi over 6 and pi over 3 multiples look slightly darker to me, just very slightly. This is one of the variations that you might see in the various different types of polar graph paper. So I've labeled the first quadrant, but I'm not going to label the second, third, and fourth quadrant. We just know that this is the next pi over 6. This is a reference angle of pi over 3. Here's a reference angle of pi over 4, and here's a reference angle of pi over 6, and so on, okay? So let's go out around 7 pi over 6 and then find a radius of 7 from that, and I'm going to use the blue pen for that. 7 pi over 6 is just past 6 pi over 6. 6 pi over 6 is pi. So if you can relate everything to pi, for example, 5 pi over 4 is going to be 4 pi over 4 plus 1 more pi over 4. 3 pi over 4 is going to be 4 pi over 4 minus a pi over 4. We're looking for 7 pi over 6, so we go to 6 pi over 6 and then go 1 more pi over 6. That's going to put us on this angle guideline right here. And then from there, I'm going to go out 1, 2, 3, 4, 5, 6, 7. My point is going to go right here. That's the point 7, 7 pi over 6 in polar coordinates. Okay, for 6, negative pi over 4, since we're doing the angle first, we need to go around negative pi over 4. Remember that negative angles are just found by going in the clockwise direction. So this is a reference angle of pi over 4, so this is negative pi over 4. So I'm going to be working along this angle guideline right here. And I need to, I'm looking for a radius of 6. I'm going to use pink for this one. So I have, on this line here, I have 1, 2, 3, 4, 5, 6. So my point's going to go right there. And I have to find it again. Every time I switch tools, 1, 2, 3, 4, 5, 6. I have to look away, so I kind of lose my reference. And that is the point. Let me make a note here. I used a pink marker for that. So I'll do the next one in green, negative 3, 3 pi over 4. And this is a little bit tricky. We're going to start with the angle. Remember that this is 4 pi over 4. So if I go back a pi over 4, this reference angle of pi over 4, I'm going to be along this angle guideline. And I want a radius of negative 3. Now this is where it gets tricky. Radiuses are not normally thought of as being negative. But if this is a radius of 3, a radius of negative 3 can be thought of as being along, let me do this, being along this line. Here's the line for, where am I, 3 pi over 4, right? So if I take that to here and then keep going to figure out which line I'm on, not that one, what the heck? Yeah, there we go, that line right there. If I go out to 3 pi over 4 and then go back 3, I'll land right here. And that's what it means to have a negative radius. 1, 2, 3. My point goes right there. So in this case, I had to go around to 3 pi over 4, and then from 0 go back 3 units. That's what it means in this environment specifically to have a negative radius. All right, now that we know how to plot coordinates using plot points using polar coordinates, we're going to look at how to get from rectangular coordinates to polar coordinates and polar coordinates to rectangular coordinates. Your textbook gives this as 2 separate subsections, so I am going to make 2 separate videos, but I think they'll probably be pretty short. Let's cross our fingers. This one was pretty long. I'll see you over there.